Section 5.6 is called Slant Asymptotes. Just when you thought we had answered and drawn as complicated graphs as we possibly could, we're about to get a little bit more complicated, because now we're going to introduce slant asymptotes. So up until now, there's been two types of asymptotes. There's been vertical asymptotes, and there have been horizontal asymptotes. Those are terrible drawings, but you know what I mean. Vertical. Look at that horizontal. That's bad. Anyway, today what we're doing is we're going to talk about slant asymptotes. Guess what they look like? They're on a slant, like this. They're also called oblique asymptotes, so it means exactly the same thing. And here's the little, well, it's not so little, but here's the definition of them mathematically. The line y equals mx plus b is a slant asymptote, right? You can see the slant asymptote's a line, and this is the equation of a line. It's a slant asymptote if the vertical distance between the curve, f of x, and the line approaches 0 as x approaches infinity or negative infinity. What does that mean? Well, I've tried to draw a function here. It's the blue, and it's called f of x, or I'll just put f. So this is the blue here and here. This is part of the function as well, right? And it looks like there's actually a vertical asymptote at the y-axis, because it's getting closer and closer and never reaching, getting closer and closer and never reaching. And then we have this slant asymptote here. And what needs to be true in order for this to actually be a slant asymptote is that the limit of f of x minus mx plus b as x approaches infinity or negative infinity, so it's a plus or minus infinity. That's awful. That says x approaches plus or minus infinity. That has to equal 0. If that's the case, then this is a slant asymptote. So, do you get what this means? It means the difference between the distance between the function and the line, function f of x, line mx plus b, we're subtracting them to get the distance between them. As you go way, way, way out to infinity, so way out to the right, or way, way out to negative infinity, way out to the left, this blue part here is getting ever so close to the red dotted line. How close? It's approaching 0. And we can get as close as we want just by going further out to the right. Same down here. We can get this blue line here, right here, as close to this red dotted line as we want, just by going as far out to the left as we want. So the limit is 0 in both those cases. In that case, we have a slant asymptote. Okay, some more important facts about slant asymptotes. They occur in rational functions when the degree of the numerator is 1 more than the degree of the denominator. So let's take a second and talk about that. We have talked before about rational functions, and if you want to look for the horizontal asymptote, I just want to remind you about this. If we had something like x over x squared, what does this mean when you have a rational function and the bottom degree is bigger than the top degree? It means that the horizontal asymptote is the x-axis. It has an equation of y equals 0. What happens when they have exactly the same, like x squared and x squared? That means the horizontal asymptote, you take the leading coefficient of numerator and denominator, divide them, so 1 over 1. So the horizontal asymptote would be at y equals 1. What happens if this one's bigger, like 3 here? That means there is no horizontal asymptote. But there could be a slant asymptote. When would there be a slant asymptote? When the degree of the numerator is 1 more than the denominator. And that's what the case is here. 3 is 1 more than 2. If this was 4 here, there would be no horizontal and there would be no slant. But if this is a 3, then there is a slant asymptote. You can get the equation of the slant asymptote by dividing, doing long division. Or sometimes you'll be able to do synthetic division. And if there is a slant asymptote, then there can be no horizontal asymptote. There could be a vertical one though. Could be a vertical asymptote. So let's find the slant asymptote of this curve right here. And we know that there would be a slant asymptote because if you look at the degree of the top, it's 3. If you look at the degree of the bottom, it's 2. 3 is 1 more than 2. Oh, we're going to have a slant asymptote. How do we find it? We divide. Now you can't use synthetic division here because you have x squared plus 1. If it was x plus 1 you could do it, but x squared plus 1 can't do it. So we have to do long division. So I'm going to write this, the x squared plus 1, I'm going to write that first, but I'm going to put x squared plus 0x, because there's no x term here, plus 1. And then that's going to go into 2x cubed. Let's make sure we have them all. Do we have an x squared? Yes. Minus 3x squared. Do we have an x? Yes. Plus x. Do we have a constant? Yes, we do, so that's all good. Didn't need to add any zeros there. And we divide. So the way we do that, we look to see what do we multiply x squared by to get 2x cubed? You have to multiply it by 2x. So right over the x, I'm going to put 2x, and then multiply. 2x times x squared, 2x cubed. These should always be exactly the same. If you don't, you did something wrong. 2x times 0, x equals 0x squared. 2x times 1 is 2x, and we're going to subtract all these terms. So 2x cubed minus 2x cubed, 0. Negative 3x squared minus 0, still negative 3x squared. X, take away 2x, is negative x, and then bring down your negative 3. What do you have to multiply x squared by to get negative 3x squared? Negative 3. Negative 3 times x squared is negative 3x squared. Negative 3 times 0x is negative 0x. Negative 3 times 1 is negative 3. We subtract all of that. That cancels. Negative x take away nothing is still negative x. Negative 3 take away negative 3, that's gone as well. So here's our remainder down here, but it's actually not what we're interested in. What we're interested in is our quotient, because this is the equation of the asymptote. So the equation of the slant asymptote is y equals 2x minus 3. That's how you would figure out what the slant asymptote is. Okay, now I won't often or maybe ever ask you this again, but it says verify here. So we have to make sure that this slant asymptote, that this agrees with this statement we made right here. It has to satisfy that. So I'm going to start by just writing down that statement again. Okay, so we're going to do this. We're going to figure out what the limit is of f of x minus mx plus b as x approaches positive negative infinity, and what we want it to equal, we don't know what it does, we want it to equal 0. That's what we're hoping for. So let's go ahead and plug what we know into this. We need to plug into here f of x. Well, f of x is this whole thing up here, the 2x cubed minus 3x squared plus x minus 3 all over x squared plus 1. So that's what I'm going to put in for the f of x. Minus mx plus b is the equation of the slant asymptote. Well, I just found that up here. It's y equals 2x minus 3. So I have to put 2x minus 3 here. And I'm going to put that over denominator of 1. Because the next thing I need to do is I need to get common denominators. Well, the common denominator of x squared plus 1 and 1 is x squared plus 1. So this first bit can stay exactly the same, all this. The denominator for all this is going to be x squared plus 1. This can stay exactly the same. 2x cubed minus 3x squared plus x minus 3. And then we're going to take away, but what I have to do is I have to multiply top and bottom here by x squared plus 1. Right? If you want, you could write it in here if it helps you remember or understand it. You've got to multiply top and bottom by x squared plus 1. So on the top here, you're going to have to do mountains and valleys, right? So we'd have 2x times x squared, which is 2x cubed. 2x times 1 is 2x. Minus 3 times x squared is negative 3x squared. And negative 3 times 1 is negative 3. Now we're going to simplify. So we got a 2x cubed, and we have a negative 2x cubed, so those are gone. We have a negative 3x squared, take away negative 3x squared. Those cancel out. This is great. We have a, let's skip to this one, negative 3, take away negative 3. Those cancel out. So all we're left with here is x take away 2x, which is equal to negative x over x squared plus 1. Now, we've got something that's quite manageable. Do you remember how to find the limits when you have rational functions? We find the biggest degree, which is x squared, and we divide everything by that. So we're going to have the limit as x approaches positive minus infinity. We have negative x over x squared divided by x squared over x squared plus 1 over x squared. So I have to write this again. It's a bit of a drag. Negative x over x squared. You can take an x out of there. So you got negative 1 over x squared over x squared is 1 plus 1 over x squared. You can't do anything. Now we can finally take the limit. If you divide 1, or any constant, by infinity or negative infinity, do you remember what you get? It approaches 0. So you get 0 over 1 plus, even squaring it, infinity or negative infinity squared is just infinity. 1 divided by infinity is 0. So you get 0 over 1, which is equal to 0. Hey, remember way back up here I said it had to equal 0? It did. So we know that this is true. That really was the slant asymptote. As I said, I'm probably not going to make you do that very often, if ever. That's a lot of work for not much payoff. Now, we're quite a ways into this video and I have horrible news. Now we're going to do one of those curves that we've been doing with all the steps. Step 1 is domain. There's no square root, so all I have to look at is the denominator. I need to make sure that x minus 1 does not equal 0, and that would be when x equals 1. In other words, x cannot equal 1. For the y-intercept, we're going to plug 0 into the x's, so you get y equals 1 plus 0 minus 0 squared all over 0 minus 1, which means you have 1 plus 0 minus 0 over negative 1, which means your y-intercept is negative 1. For your x-intercept, you have to set the y equal to 0, and we're going to solve. So you get 0 equals 1 plus x minus x squared all over x minus 1. Multiply both sides by x minus 1. This will cancel, and this stays at 0. So you have 0 equals 1 plus x minus x squared. This is good, it's equal to 0, but we'd like the leading coefficient to be positive, so let's move everything to this side. You get x squared minus x minus 1 equals 0. And you try to factor this. Two numbers that multiply to 1 and subtract to 1. Are you kidding me? You can't do it. Do you know what this means? Do you? X equals negative b. Yes, we have to do the quadratic formula. X equals negative b, so it'd be negative negative 1, which is 1, plus or minus square root b squared, well it's negative 1 squared, which is 1, minus 4 times 1 times negative 1, which is negative 4, all over 2 times a, which is 1, which is 2. So you get x equals 1 plus or minus the square root of 5 all over 2. So if we were going to summarize our intercepts, we have a y-intercept at negative 1, that means 0, negative 1, and we have two x-intercepts. One's at 1 plus root 5 over 2, comma 0, and the other one's at 1 minus root 5 over 2, 0. And needless to say, you're going to have to take your calculator out and figure out approximately what are these values equal to, because when we graph it, that's not very useful. If you put 1 plus root 5 over 2, you're going to get 1.6. And if you put 1 minus root 5 over 2, you're going to get negative 0.6. So there's our intercepts. Okay, 3 is symmetry, so we have to figure out what f of negative x is by putting negative x into the x's. 1 plus negative x minus negative x squared all over negative x minus 1. So what can we do here? 1 plus negative x, it's the same as 1 minus x. Negative x squared is just x squared, so we have minus x squared, and then negative x minus 1. Is that the same as up here? No. Is every term up here just the negation down here? No. So in other words, there is no symmetry. Okay, 4 is asymptotes. Let's start with the vertical ones. Vertical asymptotes occur when the denominator equals 0. We already found that. Denominator equals 0 when x is equal to 1. So there's a vertical asymptote at x equals 1. And what we also have to figure out then is what's the limit of this function as x approaches 1 from the left, and the limit of this function as x approaches 1 from the right. So here's our function right here. I can actually plug 1 into the top. So I get 1 plus 1 is 2, minus 1 squared is 1, so 2 minus 1 is 1. I just end up with 1 on the top here. On the bottom, a number just a little bit smaller than 1, 0.9999, take away 1, you end up with a very small negative here, which means you're going to end up with negative infinity. And then on this one, if you put 1 in there, you get exactly the same thing, 1. A number that's a little bit bigger than 1, like 1.0001, take away 1 is a very small positive. So you end up with positive infinity here. So if you were to draw that asymptote, which we eventually will, at the point 1, on the left-hand side, it's going to approach negative infinity, and on the right-hand side, it's going to approach infinity. So that'll be part of our graph right there. Horizontal asymptote, well, we've got x squared on top and x on the bottom. So when the numerator is bigger than the denominator, there's going to be no horizontal asymptote. However, we are going to have a slant asymptote in this case because the degree of the numerator is 1 more than the denominator. This is 2, this is 1, so we have to find the slant asymptote. So you can do long division, but you know what else you can do here? You can use synthetic division because the bottom is just x minus 1. This is lovely. Let's use our synthetic division much faster. So on the top, you're going to put your coefficients in proper descending order. So you should put -1 first, then you should put 1, and then you should put 1. And on the flag here, since this is x minus 1, you're going to put +1. Drag down the -1 and multiply. 1 times -1 is -1. Add, you get 0. Multiply, you get 0. Add, you get 1. So this last number here is the remainder, and that's actually not part of the slant asymptote. All we need for the slant asymptote are these two numbers. So this is your constant, and this is your x. In other words, you just get -x. The equation of the slant asymptote is y equals -x. You don't worry about remainders when you're looking at slant asymptote. Okay, it's time to take the derivative. Oh my gosh, we have to use the quotient rule, so it's going to take a while. Y prime equals, derivative of the top is 1 minus 2x. We got to multiply that by the bottom, which is x minus 1, minus the top, 1 plus x minus x squared, times the derivative of the bottom, which is just 1, and then we divide all that by the bottom squared. We're going to have to expand this. 1 times x is x, 1 times -1 is -1, -2x times x is -2x squared, -2x times -1 is plus 2x, minus, this is just multiplied by 1, so that makes no difference, but we have to change the signs of everything here because we have -1, minus x, and minus is plus x squared. Just leave the bottom the same, x minus 1 squared. Let's combine some stuff. X squareds, we have a -2x and a x squared, so it's -x squared. We have x, take away x, so those are gone, plus 2x. So we got plus 2x here, and then we have -1, take away 1, which is -2. And that's all over x minus 1 squared. Time for critical numbers. What would make the denominator equal 0? In other words, when does this not exist? Well, it doesn't exist when it equals 1, right? We already saw that, but I'll do it again just to show you. Square root of both sides, you get x minus 1 equals 0, add 1. So there you go, one of your critical numbers is 1. The other thing you have to do is you have to look for when does this whole derivative equal 0. In other words, when's the numerator, -x squared plus 2x minus 2, when does that equal 0? Again, to solve this, we probably want to move everything to the other side. So x squared minus 2x plus 2. Looking for two numbers that multiply to 2 and add to 2. There's no such numbers. You got to use the quadratic formula again. I think we're going to get lucky though, and it's not going to actually work. X equals -b, which is 2, plus or minus square root, -2 squared is 4, minus 4 times 1 times 2 is 8, all over 2, and if you look right here, you have the square root of 4 minus 8, which is -4. You can't do that, so this doesn't work, and it means the only critical number we have is 1. So that's the only number we have to put on our wiggle graph. Now, where are we going to try it out? We're going to try it out right here. The bottom's squared though, so you don't have to worry about that. You only have to worry about the top up here, because this is always going to be positive. So let's try 0 to start. That's easy. 0 plus 0 take away 2 is definitely negative. So we have negative here, which means decreasing. Let's try, I don't know, 10. 10 squared is 100, but it's actually -100 when we put that on. -100 plus 20 is -80. Take away 2 is still negative. So this is decreasing as well. Areas of increase? Never. Areas of decrease? From -infinity to 1. And also from 1 to infinity. Next thing we do is maximum minimum. Decrease, decrease, no change. There's no increase at all. There's no maximum. There's no minimum. Okay, time to take the second derivative of this boxed stuff right here. So y double prime, because this is what y prime equal, right? Y double prime. Quotient rule again. Take the derivative of the top, -2x plus 2, and we have to multiply that by the bottom, x minus 1 squared, minus the top, -x squared plus 2x minus 2, times the derivative of the bottom. Well, to get the derivative of the bottom, we have to do the chain rule. The 2 comes down. We keep the inside the same, and now this 2 drops down to a 1, but we don't have to put that. Then we take the derivative of the inside. Mercifully, the inside only has a derivative of 1. All of that is divided by x minus 1 squared, but now that's going to be squared. Now, you don't want to expand this out here because you have another x minus 1 there. But what I notice here actually is you could factor out a 2 in this first bit. So you probably don't need to do this, but I think it might be helpful. So I'm going to take out a negative 2, and what I'm left with is x minus 1, which is great because that's also what I have here is x minus 1. So why don't I save a step? This is x minus 1 here and 2 more x minus 1s there, so I end up with 3 of those. I hope that makes sense. I've just factored out the 2 and I was left with an x minus 1 multiplied by this. Now I have 3 of them. Okay, then I have 2 times 1 is 2, so I have minus 2 x minus 1, and then I'll rewrite all this negative x squared plus 2x minus 2, and that's all over x minus 1 to the 4th. Squared, squared, got to multiply those, it comes to the 4th. Okay, take out a greatest common factor from this bit and this bit. So the greatest common factor would be negative 2 shows up in both of them, and also x minus 1 shows up in both of them. And what's left in the first part here is another x minus 1 squared, plus this is gone, so it's just this that's left, negative x squared plus 2x minus 2, and that's all over x minus 1 to the 4th. Great, this will almost always happen. You have x minus 1 and x minus 1. This will drop down to a 3. So now you're going to need to expand this. So we have x minus 1 squared. That equals x squared minus 2x plus 1. And then we still have all this, negative x squared plus 2x minus 2. That's all over x minus 1 cubed. And I think we get to cancel some stuff out. X squared, negative x squared. Negative 2x plus 2x. We have 1 minus 2, which is negative 1. Well, negative 2 times negative 1 just equals 2. So finally we end up with 2 over x minus 1 all cubed. This is our y double prime. It's time to find our pips. So to get the pips, we have to see what would make the denominator equal 0. In other words, when does this not exist, this second derivative? Well, that would be when x minus 1 cubed equals 0, cube root of both sides, and then add the 1. So x equals 1 is one of our pips. We also need to look at when would this whole thing equal 0. So you want to know when does 2, the numerator, equal 0. That doesn't make sense. It never does. So this is our only pip. The only potential inflection point is 1. So we're going to test this out right here. Okay, let's start by trying 0. 0 take away 1 is negative 1, and negative 1 cubed is still negative. 2 divided by negative is negative. So this is concave down. Let's put 2 in here. 2 take away 1 is 1. 1 cubed is still 1. 2 divided by 1, that's a positive number. This is concave up. So concave up, concave down, inflection point. Concave up from 1 to infinity. Concave down from negative infinity to 1. Inflection point? Yes, because it goes negative plus. There's a change there. So it's at the point 1 comma something. We got to try that back in the original function way up here. I'm going to put 1 in there. Wait a minute. 1? We said it couldn't be 1. There is no inflection point because 1 is not part of the domain. Whoa, almost made a mistake there. So actually, there is no inflection. Okay, we're ready to draw this thing. So ridiculous how long this took. Asymptotes were at x equals 1, and our slant asymptote was at y equals negative x. And y equals negative x is this 45-degree angle like this. Points that we know our y-intercepts at 0, negative 1. And our x-intercepts were at 1.6 and negative 0.6. So 1 point at 1.6, which is around here, and negative 0.6, which is around there. The other thing we can do is draw in this right here. So near the asymptote, the vertical asymptote, it goes up towards infinity, and it goes down towards negative infinity. Below 1, it's concave down. So it's got to be concave down all here. Remember, this was always decreasing except for at the asymptote. So we want it to be always decreasing, and we want it to be concave down here. If it comes closer and closer to the asymptote here, as it should, and then this is all concave down, and it's all decreasing. This is terrible drawing, but hopefully you get the sense. And then this needs to be concave up over here and also decreasing, so that would look like this, coming through here, and then like that, and getting closer and closer to this asymptote there, but never reaching it. So that is our crazy drawing right now. Want to see the real thing? There it is. Again, somewhat close. Pretty good job. Amazing what you can do using calculus. Too bad that it takes so long.